Good morning. This is Engineering Statistics and Linear Algebra, 18 EC44, Module 4, Lecture 11, Orthogonal Vectors and Subspaces. I am Dr. Noorullah Sharif, Professor and Head of CCAB Institute of Engineering and Technology, Vijaypura. I am using the slides which are prepared for Linear Algebra and Random Process LARP/2018, that is CS6015. Whose link is present over here, which is part of the Visualization Perception Lab of the Department of Computer Science and Engineering in the Institute of Technology at Madras, India. So first, let us see some details about the vectors which you have already considered, which is basically an algebraic approach. So we have here an n-dimensional coordinate vector, which is an element of Rn, and that can be written as an n tuple, which is x1, x2, xn of real numbers. So we can consider two different vectors, A and B. A with again n tuples, A1, A2 AN, and B equal to B1, B2 Bn. So if you consider these two, then the an element R belonging to R will be, you can consider another scalar R belonging to R there, and then by definition we can consider the addition as well as the multiplication by addition of the vectors and multiplication of a scalar R with a vector and all the other properties which the vectors should satisfy for the vector space is what we are considering over here. So by definition, you can add A plus B, and that will give you each of the corresponding element getting added together. That is A1 plus B1, A2 plus B2, etc. In the same way at the end, AN plus Bn. Similarly, you can multiply the scalar R with any of the vectors A and B. So here we are considering that R is multiplied with A, and then R gets multiplied with each of the components or tuples there. That is R into A1, R into A2, R into AN. Then a zero vector is represented by a n tuple, which is 0, 0, 0, 0 till the n elements. Similarly, you can just negate either of the vectors A and B. So that is minus B is equal to each of the tuples get negated. That is minus B1, minus B2, etc. You can as well subtract the vector B from A or vice versa, wherein it will be just a combination of addition of vector A with the negation of the B. Then we have just each of the tuples being subtracted. That is A1 minus B1, A2 minus B2, AN minus Bn. Then coming to the Cartesian coordinates, we see that you can specify a origin 0. Once we specify a origin 0, then each point A is associated with a position vector 0A, OA, and that is the vector. Consequently, every vector has a unique representation with the tail at the origin. So that means if we consider the point over here 2, 1, then that 2, 1 is with respect to the origin which is there over here, and this is the vector. If this is the A, then this is the vector which corresponds to A. Similarly, if you have a point B which is something like this, then this is with respect to the origin over here, and again the vector which is mentioned by this, which we can now call it as OB, will be corresponding to this value. So Cartesian coordinates allow us to identify a line, a plane, a space within which belongs to R, R square, R cube respectively. So these are just one-dimensional, two-dimensional, and three-dimensional spaces. Then we come to the length and the distance. So by definition, the length of the vector v, which is v1 comma v2 dot 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 vn, which belongs to Rn, that is the n-dimensional space, is mentioned over here as the double mod of v equal to root of v1 square plus v2 square plus dot 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 vn square. The distance between two vectors or points x and y can be written as double mod of y minus x. The distance between 2 points x and y, or two vectors x and y, can be written as double mod of y minus x. Then we have properties for the length. The length of any vector is always greater than 0. It will be 0 only if x equal to 0. Always greater than or equal to 0, and it is equal to 0 only if x equal to 0. Then the length of the Rx will be equal to the length of x multiplied with the, so to say, mod of the scalar. The scalar should again be multiplied by, scalar should always be converted into a positive quantity, and hence we'll get the rest of it. So that is known as homogeneity. Then the length of a vector, which is the summation of two different vectors x and y, can be considered as less than or equal to the sum of the lengths of each of those vectors. So this is a triangle inequality. Then we have the scalar product. By definition, the scalar product of two vectors x and y, x again in the n dimension as x1 to xn and y in the n dimension from y1 to yn, can be represented as x dot y is equal to x1 y1 plus x2 y2 plus dot 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 xn yn. So we have certain properties of the scalar product. X dot x will always be again greater than 0, and it is equal to 0, greater than or equal to 0, and it's equal to 0 only if x equal to 0. Then we have the symmetrical property, that is x taken the dot product with y is equal to y dot product of x. That is known as symmetry. Then we have the distributive law, wherein if you have x plus y as the sum of two vectors, and that is taken with the dot product of z, then that is equivalent to taking the dot product of x and z together and adding to the another dot product of y and z together, and this is known as distributive law. Then homogeneity is if you have a vector x and you multiply that with a what you call scalar constant r, and then take the dot product of y, that is equivalent to having the dot product of x and y, two different vectors, and then multiplying it with the scalar which is known as r. So one should remember that this scalar product x dot y is almost same in the matrix as xt, the xt into y, that is x transpose into y. Then we have this inequality which is known as the Cauchy-Schwarz inequality, that is written as the modulus of the length of x dot y is always less than or equal to the multiplication of the lengths of each of those vectors x and y, and that is represented by the what you call equation cos theta is equal to x dot y divided by the length of x divided by the length of y for a unique 0 less than or equal to theta less than or equal to pi. So theta is the angle between the vectors x and y, where theta is the angle between the vectors x and y. If theta is equal to 0, then both the vectors x and y will be in the same what you call line. It will be within the same line, or you can say same space, more particularly in the same line. The vectors x and y are said to be orthogonal. The vectors which we are taking over here, x and y, are said to be orthogonal. If they are orthogonal, then naturally their dot product will become equal to 0. So perpendicular to each other if x dot y is equal to 0. So theta is equal to 90 degrees. That means here you have 90 degrees. Cos of 90 degrees will give us the value which is 0. So x dot y will be equal to 0 at that time. So x dot y will be equal to 0 will give us theta is equal to 90 degrees. So the definition for orthogonality just means that x dot y is equal to 0, and that will give us the angle which is 90 degrees. So if you want to find the angle between two vectors which are x equal to 2 comma minus 1 and y is equal to 3 comma 1, we can just take the dot product of these two, and naturally 2 into 3 plus minus in 1 into 1, that will be equal to 5. 6 minus 1 equal to 5, and that is what is specified. The length of this is 2 square root of 2 square plus minus 1 square, that will be root of 5. The length of this is root of 3 square plus 1 square, that is root of 9 plus 1, that is root of 10, and that is specified over here. So cos of theta will be this quantity divided by this into this, and that is 5 divided by root of 5 multiplied by root of 10, and that will be 1 by root 2. And because cos theta is 1 by root 2, then theta will be naturally 45 degrees. Similarly, you can find an angle phi between two vectors minus 2, 1, 3, and w v equal to minus 2, 1, 3, and w equal to 4, 5, 1. So whereas these are vectors in our square, okay, in the vector space R square, these are vectors in the vector space RQ. So if we try to take the dot product of this, minus 2 into 4 is minus 8, 1 into 5 is plus 5, 3 into 1 is plus 3. If you add all those three things, you'll get a dot product which is equal to 0, and hence if you substitute it over here, x dot y is equal to 0, or v dot w is equal to 0, then we'll get cos of theta is equal to 0, and theta will be equal to 90 degrees. Then we come to the definition for more proper definition of the orthogonality. So if you have two vectors x and y which belong to the vector space of n dimension or n dimension vector space, then they are said to be orthogonal, denoted by the symbol if x dot y is equal to 0. This is what we have considered. The second definition is with respect to a vector x is said to be orthogonal to a non-empty set y. So here we are considering a vector, and here we are considering a non-empty set y, which belongs to Rn. A set belongs to Rn, whereas a vector always, is a set y is a subset of Rn. A set y is a subset of Rn, whereas a vector x belongs to Rn. So denoted by, again, x perpendicular with y if x dot of y is equal to 0 for any y belonging to capital Y. Any vector y belonging to the non-empty set capital Y. And this is generally denoted by x dot y is generally denoted by x transpose into y in terms of matrices also. The third definition is when both, we have non-empty sets x and y, which are subsets of the n-dimensional space, are said to be orthogonal, denoted by x in perpendicular to y, or orthogonal to y, if x dot y is equal to 0 for any x belonging to x and y belonging to y. So this x belongs to a non-empty set x, this y belongs to a non-empty set y. So again, considering some of the examples, if you have a line which is x equal to y equal to 0, then it just means the vector is 0, 0, x and y are 0, 0, and some value for z. And if you have another line which is y equal to z equal to 0, a line which is y equal to z equal to 0, then we don't know what is the value of x there. So therefore, that is specified by w, another vector w, with x 0, 0, y 0, and z 0, x is some value. Now, if you take the dot product of this, v dot w, you'll get 0, 0 into x is 0, 0 into 0 is 0, z into 0 is 0. So the dot product is 0. Therefore, the V and W, the two lines are orthogonal to each other. Then we can consider another one wherein the line x equal to y equal to 0 and a plane which is z equal to 0. So a line which is x equal to y equal to 0 can be specified by a vector v equal to 0, 0, z, and a plane with z equal to 0 can be specified by a vector by means of writing xy of 0, z is 0, and both xy are present, therefore it's a plane. Here xy are 0 and only z is present, therefore it's a line. A single value is present, therefore it's a line. Both are present, or these two are present and this is not present, therefore it's a plane. If all the three are present, then it will be a vector in the three-dimensional space. Then v dot w will be equal to, again, if you want to take the dot product of this with this, 0 into x is 0, 0 into y is 0, z into 0 is 0, add all of them, we'll get a value which is 0. Similarly, you can have another line x equal to y equal to 0 and a plane which is z equal to 0. A line which is x equal to y equal to 0 is v equal to 0, 0, 1, and a plane which is z equal to 1 is specified by the value x, y, comma 1, x, comma y, comma 1 as w. And if you again take the dot product of them, if you take the dot product of them, then here he's what you call, if you take the dot product of them, then they will not be orthogonal to each other. The vector v 0, 0, 1 belongs to both the line and the plane. V dot v is equal to 1, which is not equal to 0. Then we have the orthogonality and geometric interpretation over here. So we can consider the figure on the left here. This is the dot product of two vectors x and y is equal to 0 because they are perpendicular to each other. This is the vector x with value for 2. This is the vector y with value -1 and 2. The length of this is naturally 5. The length of this is root of 4 square plus 2 square, that is root of 20. They are perpendicular to each other, and that can be considered as, again, considering the dot product of each. That is 4 into -1 is -4, 2 into 2 is +4. Adding both will give us the value 0, and hence that gives us a dot product which is equal to 0. This shows that the two vectors are orthogonal, they are perpendicular to each other. So this can always be specified by means of the x transpose y. So you can take the transpose of the y, transpose of x, and that will be a row matrix with 4 and 2 as its elements in the two columns, and the y matrix which is as it is -1 and 2, and if you take the multiplication of that, again you are going to get the value 4 into -1 plus 2 into 2, that is equal to 0. If the xty is greater than 0, then the angle between the two vectors is less than 90 degrees. If this turns out to be positive, then the angle is less than 90 degrees. If the angle, if the what you call, this turns out to be the xty, which is the dot product, turns out to be less than 0, that is negative, then the angle between the two vectors is greater than 90. So if the dot product is greater than 0, that is positive, then angle between the two vectors is less than 90. If the dot product is less than 0, that is negative, the angle between the two vectors is greater than 90. So we have a theorem here. If we have non-zero vectors v1 to vk, which are mutually orthogonal, every vector is perpendicular to every other vector, then those vectors are linearly independent. So the proof for this can be considered something like this. So suppose we write C1 V1 plus dot 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 CK Vk is equal to 0. To show that C1 must be 0, take the inner product of both sides with V1. Orthogonality of C leaves only one term. So V1T, V1 is the only one which is there, which is orthogonality of that will be V1T multiplied by the vector which is C1 V1 plus C2 V2 plus dot 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 CK VK. Then this dot product with this will just give us the value V1T dot product V1 will be equal to V1 dot product V1 will be equal to 1. So we are left with the value C1. So that means, if you multiply this, you'll get C1 V1T V1 equal to, because this quantity is 0, you'll get this as 0. And this gives us that the, what you call, this cannot be 0, this is equal to 1. Rather, the vectors are non-zero. So V1T V1 is equal to, not equal to 0. This should have been not equal to 0. And therefore, C1 is equal to 0. So this is equal to rather 1, or it might be a quantity which is definitely not equal to 0, and hence C1 should be equal to 0. The same is true for every CI. That means you can multiply with, again, you can take the what you call dot product of V2 with this and then try the same. Then you'll get C2 V2T V2 equal to V2 transpose V2 equal to 0. Again, V2 transpose V2 is not equal to 0. It is a quantity which is equal to non-zero quantity, and therefore the C2 should be 0. So each of the CIs are equal to this. So the only combination V produces 0 has all CIs. All the CIs are 0, which will produce the value of this equal to 0. This shows that vectors are linearly independent. In general, the coordinate vectors E1 to En in the Rn are most important orthogonal vectors. So E1 is the first element 1 with all the other zeros. E2 is the second element 1 with all the other zeros. And similarly, En is the last element, nth element is 1 with all the other zeros. In Rn are most important orthogonal vectors. These are the columns of identity matrix, and they form the simplest basis for Rn. We see that E1 to En form the simplest basis for Rn, and they are unit vectors, and each has a length 1. Ei, mod of Ei, or length of Ei is equal to 1, and they point along the different coordinate axis. They point along the different coordinate axis. So say in the 2-dimension, they might be pointing towards x and y. In the 3-dimension, x, y, z. If these axes are rotated, the result is a new orthogonal basis. You can just rotate this axis by some value. You will result in a new orthogonal basis, a new system of mutually orthogonal vectors, because all of them are rotated by the same amount. In R square, we have cos square theta plus sin square theta is equal to 1. And therefore, the orthogonal vectors in R square might be V1 equal to cos theta sin theta, and V2 might be minus sin theta cos theta. So you multiply this cos theta with minus sin theta, you'll get minus cos theta sin theta. And if you multiply sin theta with cos theta, you'll get plus sin theta cos theta. Add them up, you'll get a value which is 0. So they should be orthogonal to each other. So for today, we'll stop at this. We'll continue in the part 2 of the lecture.